All right, so we've done some basic factoring already, and today we're going to talk about factoring special cases. And remember, the whole purpose of us doing the factoring or the factored form is so that we can find the factors and then find the roots. So the three problems that we have here are ones that we've already done before. They're all related. I just want to remind us of what the differences are. And the first one is really easy. We're trying to pick two numbers that multiply to 4 and add to give me 5, and that's 4 and 1. So if I write my two cases, that gives me x plus 4 and x plus 1 as my factors. And that would be the final answer as far as factors go. In this second example, remember, 2 is not a GCF here. I can't take a 2 out of every single number, so instead I've got to move this 2 to the end. And when I do that, it creates the problem x squared plus 5x plus 4, which you'll notice is the same problem that we had up at the top. So I know I'm going to start with the same factors, except on these, remember from what we did today, we've got to divide the 2 to fix it. So if the 2 divides, that would give us the answer x plus 2, like the first factor, because 4 divides by 2. But in the second one, we'd have to do bottoms up and get 2x plus 1. So notice that even though these problems have a similar point, the two factors at the end are very different, which is going to give us different roots. All right, and then the last example, again, we've already looked at something like this. In this last one, we actually can divide a GCF out. So we can do a GCF of 2, which is going to give us the problem x squared plus 5x plus 4, which has the same factors as both of the problems above. So I know I'm going to have a factor of x plus 4 and x plus 1, except here, because there's a GCF, just like with the GCF when we did completing the square, it's going to go to the front. So this GCF right here is going to track to the front of my answer. So that answer is going to be 2x plus 4x plus 1. So kind of keep these in mind. All three of those you should be able to follow and kind of make sense of, and definitely be able to do. And let's look at what's different about some of the patterns that we're going to see today. All right, so here's our first weird case. Some of this problem you might recognize right away, and that there is a GCF that I can take out of all three of these. So the difference is, well, a few things that are different. One, 6 is not the GCF. I can't take 6 out of all three of these numbers, but I can take something out. And what I can take out is a 2. Okay, but also it should strike you as a little odd that there's an x to the third. Notice that all three of these have an x in them, so the GCF is not only the number 2, but it's also x. All right, so when I rewrite my problem, then that's going to give me, let's see, 3x to the third, not to the third anymore, I'm sorry, squared, right, minus 8x plus 4. All right, so now I'm back to a problem that I know how to do. Now I have no more GCF, so I've got to take the 3 to the end, which is going to give me x squared minus 8x plus 12. Pick my two numbers that multiply to 12 and add to give me negative 8, and that's going to be negative 6 and negative 2. So my factors to begin with are negative x minus 6 and x minus 2. But don't forget, we took the 3 to the end, so we've got to bring it back. So divide by 3. 6 does divide by 3, which is going to make this first factor x minus 2. And the second factor, 2 does not simplify with 3, so the 3 is going to come up, 3x minus 2. Now remember, GCFs, we've got to bring the GCF down. So I also have this 2x in the front. So this is my factored form. And from this, remember, you've got, I can't remember if I said this to you in class today, but you need x to the third, and notice that I have 3 different x's here. Now, the difference with this is when we go to name the roots, where we should have 3 roots this time. Okay, so I'll name the easiest ones first. If we look here in this bottom, in the middle, that root's the easiest to name, and that's 2, 0. Remember, if you've got a number in the front, you should probably look up a step because you're going to have a fraction as a root. So this is 2/3 0. Now, where most people make their mistakes is they think about this and they try to say -2. This x is standing alone, and anytime x is standing alone, it's like you have x plus 0, which means your root is at 0, 0. So anytime x is standing alone, the root is at 0. I would put a big star in my notes with that right next to it. Rewind if you need to write that down again. Okay, here's our case 2. Now right off the bat, this might not look any different to you, and if not, that's a good thing. So we're going to start by moving the 4 to the end because I can't take anything out of all 3 of those numbers. So that's going to give me x squared minus 12x plus 36. So I'm looking for 2 numbers that multiply to give me 36 and add to give me -12. And if I think about that, those 2 numbers should be -6 and -6. So that's x minus 6 and x minus 6. And then remember, we took the 4 to the back, so we've got to bring it back around, divide by 4. Like we spoke about today, you should try to simplify that fraction if you can. 6 does simplify with 4, and that's going to become x minus 3/2 in both cases. And then, since that doesn't simplify all the way, we've got to do bottoms up, which is going to make my final answer here, let's see, 2x minus 3 and 2x minus 3. Now you may say, well, that doesn't seem like necessarily a special case, but what I want you to see is that those 2 are the same exact thing. So sometimes you may see the answer written as 2x minus 3 squared because it's the same thing twice, so that's for the factor. And then for the roots, this is going to kind of come in important next week. For the roots, it's the same root twice, so that's going to be 3, 2, 0, and 3/2, 0 again. We call this, if you'll put a little star in your notes, we call this an example of a double root because it's the same thing twice, which means this graph, when we talk about roots where it hits the x-axis, a double root touches the x-axis and turns right back around. So it doesn't ever go through the x-axis, that's like a bouncing point. So I would have a star in your notes that calls this a double root. All right, and here's our last example is where we're missing, I called it B because that's the ax squared plus bx plus c. You're just missing the middle. And if you remember, there was a special type of thing that we learned about when we were multiplying called conjugates. So anytime you're missing the middle, and I say that because I've got an x squared and a constant, but I don't have any term here that's like something x. Anytime you're missing the middle, that means it must be conjugates. Okay, and if you remember, conjugates, there were 2 things that were special about them. When they multiplied, the middle cancels. So we're going to remember this. Conjugates, when you multiply, we said 2 things. The middle cancels, and you always get subtraction. All right, so because the middle is missing here, and because I have a subtraction sign, I know that to factor this, it must have been conjugates to begin with. All right, so the quick way to factor these is to just go ahead and say, how can you break 16 apart? Because conjugates have to be the same thing in the front, right? So how do you break 16x squared apart? And that would be 4x and 4x. And then how do you break -25 apart? And conjugates have opposite signs. So one of those is +5 and the other one is -5. And that right there is your factor. Just so you see one more, another example in this would be, you could pick any square number that you wanted to. So I could do, let's say 9x squared minus 1. I know that works because it's got subtraction in the middle and the middle is missing. So my 2 factors are going to be 3x and 3x when I split the 9 apart, and then +1 and -1. And then you can still go back and do roots like you normally would, but that's how you get factors for both of those cases. And this case is called, you should know the word conjugates, but officially if you ever see it, it's called difference of squares. And they call it that difference because you're doing subtraction, and squares because the numbers that they give you are always going to be perfect square numbers.